So thank you everyone for joining us today. I'm Yang Ying from UCSB. It's my great pleasure to introduce our speaker today, Dr. Jeremy Qiu. And I think we all know Jeremy. He's an assistant professor of mechanical engineering from University of Nevada, Las Vegas. And he obtained his bachelor's degree from University of Michigan and his PhD from MIT, working with Dr. Evelyn Wan. And he obtained his postdoc training at Princeton University. And his research area covers a lot of different directions, including water, energy, nexus, phase change heat transfer, absorption of surfactants and hydrogels. So and his work has been published at many journal articles, and he's recently also is recognized by the NSF Career Award. So with that, without further ado, let's welcome our speaker, Dr. Jeremy Qiu. So Jeremy.
Thank you, Yang, for the kind introduction. Can everybody hear me? Just want to make sure I'm not muted. Okay, perfect. Okay, so today I'm going to be talking about a couple of different projects, two very different projects that I've been working on here at UNLV. Those of you who don't know me, and I do see quite a lot of familiar faces and names, so so that's good. But if you don't know a little bit about me, my background's primarily in liquid vapor phase change heat transfer. But I also look at mass transport in general. So that could be like liquid transport, vapor transport, chemical species transport. I look a lot at wetting interfacial phenomena and how you can modify that with surfactants. And I look at soft matter in general. And a particular material system I'm going to be talking about today is hydrogels. So I'm a little bit of I'm definitely mechanical thermal engineer, but I'm also kind of half a chemical engineer as well. And some current projects that I have going on, our surfactant enhanced boiling, which I'll talk about. I also look at a lot of time-dependent wetting phenomena, meaning how you could change that over time, either through diffusion of surfactant or diffusion of water through hydrogels. But I won't be talking too much about that today. And then the sort of final topic that I'll talk about is hydrogel transport and mechanics, particularly for a water harvesting application. So let me first talk about my thermal project, which is on boiling. And the way I like to think about where I might sort of fit in, I think about traditional thermal science, right? Thermodynamics, fluid mechanics, heat transfer. And thermal science was incredibly important, historically brought about an industrial revolution. But if you really think about it, a lot of our technologies haven't changed fundamentally since the Industrial Revolution, right? This is a boiler from the 1800s. This is a sort of modern boiler. Practically speaking, there isn't a whole lot different, right, in terms of the actual mechanism of heat transfer. Now, one way I think about improving boiling performance is using chemical additives. Now, a lot of you are familiar with modifying surfaces, adding micro and nano features, and obviously that does a lot of good things to boiling. You can increase the heat flux, and you can also increase the CHF. But I look at how you could do that without doing any surface modification, but just adding surfactants, which are these chemicals with hydrophilic heads and hydrophobic tails, to the bulk liquid water. And that can enhance your heat transfer coefficient a lot of times. But also a lot of times we've noticed that can lower your CHF. And I'll talk a little bit why that might be the case. Now, this is not a new topic. People have been looking at this for a couple of decades. And what we generally know is that the effective enhancement increases with the concentration. So the more you add, you shift your boiling curve to the left. And if you look at some of the early papers, they mention a lot of different phenomena happening, right? So there could be dynamic surface tension, there could be Marangoni effects, something wettability. There's a million different reasons why, people will say surfactants change the boiling behavior. But basically, if everybody says it's everything, then it means that this is a difficult and complex problem and nobody really knows anything at all, right? So this is was sort of my mission, in my PhD, to kind of find some sort of clarity. So if you don't know my previous work, I basically looked at using charged surfactants in electric fields, and what we were able to do is directly change the amount of surfactants that's absorbed to solid-liquid interfaces. And by doing that, you can change the wetting behavior on the fly, specifically on the solid-liquid interface. We don't change anything on the bulk, right? Because that electric field is such a localized effect to the surface. And what we can do is if we bring in surfactants to that surface, we make that surface more hydrophobic, which we verified through contact angle experiments, and we can enhance nucleation, right? And so it's sort of a temporal control and a spatial control of boiling. So we identified the importance of the solid-liquid interface, right? Absorption. But there's still so many lingering questions on what surfactants are doing. One of the key questions, right, to somebody, a practitioner would be like, how much surfactant do I add? And, because if you look at the literature, if you add some amount of surfactant, that's a good thing. But if you add too much, it can actually degrade your performance. You actually get a shift of your boiling curve to the right, where you get a much lower heat transfer coefficient. So there's a lot of mixed results in the literature. Another question is like, what surfactant should I use? Does the surfactant type matter, right? One way we can characterize the behavior of different surfactants is we call the critical micelle concentration. And that basically is the concentration below which you don't have any micelles, right? You just have single monomers flowing around. Maybe you have a little bit of adsorption. But once you reach the CMC, your interfaces start to get filled up. And then greater than the CMC, you start to form these aggregates where these micelles bunch together and form these micelles. And these CMCs are really an equilibrium property, meaning if you put surfactants and you dissolve them in water, you have to kind of wait some time for them to form these micelles. And if you read the literature, a lot of people will say, okay, well, CMC is very important, but we had our doubts about that, and I'll explain that in a couple of slides. But first, I want to introduce how we quantify enhancement, right? There's a lot of different ways we can do that. We generally see that a boiling curve will shift to the left, and we're going to be looking at initially at the low heat flux regime, right? So below 40 watts per centimeter squared or so. So clearly in the nuclear boiling regime. And generally, when you add some surfactant, you have a shift to the left. So we define a relative heat transfer coefficient, which is basically a ratio of how much of the delta T's, right, of the superheats, how much you're shifting it to the left, right? So a higher RHTC means that you have more of a shift in your boiling curve to the left. Now, if you read a lot of the literature, including what I said 10 years ago in a paper from 2013, I certainly believe this up to a couple of years ago, that I would have told you, and anybody would have told you, that the optimal concentration to add for a surfactant is around the CMC. So if you take any surfactant, and CMC could vary orders of magnitude, right? So you have here TW40, which is between 40, that has a CMC of around 10 to negative 2 versus S10S, which has CMC, above 20 or 30. I would have told you that the best concentration to use was whatever the CMC is for that particular surfactant, and that can vary so much, many orders of magnitude. But if you looked at how all these studies were performed, they either cited somebody else, or they looked at only a few different surfactants in a very limited concentration range. So if you look here on the bottom right, you can see these sort of bars, and those are really the small shared concentration regimes that all of these studies studied. Nobody really took a whole bunch of different surfactants and looked at it over multiple decades of concentrations. And so what we did here in a work that we published last year, we looked at 5 different surfactants, and we looked at the largest mutual concentration range. We varied concentration over 4 decades of concentration. And we wanted to test this conventional wisdom. Is the optimal heat transfer coefficient really around the CMC? So in our lab, we do, pool boiling experiments. We have a couple of different setups. One is, the one on the right is our sort of standard heat from the bottom through a copper rod, and we can measure heat flux accurately with multiple thermocouples. And we can reach a very large heat flux range, of well over 100 watts per centimeter squared. And, but this boiling chamber typically takes a lot of time. Those of you know how long pool boiling experiments take, they can be several hours. So we devised a rapid pool boiling apparatus on the left, which is a cylindrical system. And basically we can go through boiling curves, very quickly within a few minutes. There's very little thermal mass. It does limit us to a certain heat flux range, but we just wanted to just characterize enhancement and not necessarily CHF. So, we mixed it up with a lot of different types of boiling experiments and a lot of different surfactants. And what we generally see is that no matter what surfactant you use, whether it's a low CMC surfactant or a high CMC surfactant, right? You can see on the bottom here, I'm plotting all the CMCs for these 4 surfactants, and they range several orders of magnitude here. And generally speaking, qualitatively, if you look at it, the boiling, the bubbles tend to change right around 0.1 to 1 moles per meter cube, or 0.1 to 1 millimoles per liter. This is all at 15 watts per centimeter squared. Some of these pictures are cloudy because the solution actually phase separates and becomes a cloud point, so you can't actually see through it. But for the systems where you can see through it, the bubble behavior is very similar, right? Give or take within a single order of magnitude, you generally see changes around 0.1 to 1. So this started to give us an evidence that the CMC may not be playing that of an important role. Maybe it's just the absolute molar concentration. And so when we did all of our heat transfer experiments rapidly over 5 different surfactants at a lot of different concentrations, what we found is that rather than having separate peaks where each optimum is near its CMC, we actually see kind of more of a universal peak range, somewhere around 1 to 10 millimoles per meter cube. So this totally defies conventional wisdom. So when my student gave me these results, I was like, you got to redo those 150 experiments again that you did, right, where you repeated every concentration 3 times, because that can't be right. But then, he was like, oh, I don't want to do those experiments again, so let's think about what's actually happening. So if you can look at all these curves, what we saw is that, okay, there is some kind of ramp up, and they're all kind of doing the same thing. There's some kind of enhancement here to the relative heat transfer coefficient, and then we have some kind of degradation. Now, we thought about what could be happening. Well, what we do know about any kind of surfactant in liquid system is that they adsorb to interfaces, right? So if I create an interface, surfactants in the bulk will diffuse to an interface, right? Whether it's a liquid vapor or a solid liquid interface. You can do some scaling analysis here, dimensional analysis, and you can find that there's a characteristic length scale associated with this. And that's gamma EQ, gamma being the surface concentration at the interface, the equilibrium surface concentration. And you divide that by the bulk concentration. That gives you a length scale. And this has been studied before decades ago. So this is known. And so if you take that characteristic length scale, you divide square, and you divide it by the diffusion coefficient of the surfactant, you can get a diffusion timescale. So you can get an idea of how long it takes for surfactants to adsorb to an interface. And if you notice here, so you have concentration C infinity on the denominator here squared. So that means that the more surfactant that I have in the bulk, the quicker diffusion is to an interface. And gamma EQ for most surfactants don't really change within an order of magnitude. They're about 10 to the minus 6 moles per meter squared. So that's pretty constant along among many, many different types of surfactants, but the concentration can change many, many orders of magnitude, meaning your diffusion timescale can change many orders of magnitude. So what we hypothesize is that, okay, I have bubble nucleation and growth happening, and the bubble lifetime, can vary, but let's say it's something around 20 milliseconds, right? And that's pretty common for something on the order of 10 watts per centimeter squared. But that's more or less fixed. There's obviously going to be some variation with wettability changes and all that, but let's say it's on that order, about tens of milliseconds. That means that over the lifetime of that bubble, which is a certain limited amount of time, you're going to have a limited time window for surfactants to diffuse to that interface. And within that time scale, right? So if we have more surfactants, then that absorption is going to be a lot faster. And so at higher molar concentrations, we expect more surfactants to be at the interfaces, and that generally coincides with more enhancement. And so we did these studies with pendant bubble experiments, and we looked at dynamic surface tension. We modeled dynamic surface tension using the 𝗕𝗲𝗵𝘃𝗶 equation. We did all this analysis. And what we were finding is that surfactants of very different CMCs, when you look at very fast times, they actually adsorb to the interfaces very similarly. And that's because you're at a time scale where equilibrium doesn't matter. It's all time limited dynamic, it's transport limited, right? So it's diffusion limited time. And so if you look on the right here, if we look at that blue shaded region, that's kind of the bubble lifetime. And we're looking at dynamic surface tension, right? How much that surface tension drops as a function of time. And you can see what we model for all the surfactants that we tested, they all drop very, very similarly as within that blue timescale. It's really at longer timescales that you start to see differences in their equilibrium behavior. So when we modeled the actual absorption, right now here on the left, and we compared that to the absorption, assuming you have a 20 millisecond bubble, what we expected is that, okay, for that 20 millisecond bubble, the higher concentration that we get and the more absorption that we get, that seemed to coincide with that increase in relative heat transfer coefficient that we got. The other thing we noticed is that the location of that peak is right around where, if we look at the ratio of the bubble timescale to the diffusion timescale, that's right around where that ratio is 1, right? So if that ratio TB over TDiff is less than 1, we expect diffusion to be very slow. But if that ratio is greater than 1, we expect diffusion to be very fast, right? And we expect these interfaces to be very full. Now, one thing that we're a little bit concerned about is like, okay, well, shouldn't the enhancement just continue on forever, right? Like we see the absorption kind of plateau. Once you get to high enough concentration, these interfaces are full. Why don't we see a plateau in our heat transfer coefficient? So that's where we came up with our second idea. Okay, well, the more stuff that we add to the solution, the more the viscosity is going to be increasing. With higher viscosity, it just means it's harder to grow bubbles faster. There's a lot of boiling correlations out there, but if we look at the Rosenthal correlation, we know that the heat transfer coefficient is proportional to the viscosity inverse squared, right? So the more viscous it is, your HTC degrades. And so indeed, we looked at viscosity. We took two very different surfactants with very different CMCs, and we saw that their viscosity increase coincided with when these RHTCs, these relative heat transfer coefficients, started to go down. So we wanted to make sure that we had everything, whether this is the right idea to do some sort of quantitative comparison. So we came up with a power law, which combines the enhancing effect of adsorption and the degradation effect due to increases in viscosity, right? We just have two sort of fitting parameters, right? We expect these parameters to be positive, if our idea is right. Right. And so we compared all of our experiments. And then within, some healthy region of confidence or a region of uncertainty, we can sort of fit all of our data to this scaling law. Now, this scaling law is purely empirical, right? We're not really saying anything about like why it has this particular functional form. What we set up was that we know that the adsorption has to be enhancing and the viscosity has to be degrading. And this gives us some evidence that that must be the case, at least among the 150 different concentration and surfactant type combinations that we've tested. Now, one thing that and this work was, published last year in Scientific Reports, something that we're working on right now is trying to understand what is the change in CHF, right? So we know that the CHF will degrade, it will go down in concentration. But what we're also noticing is that drop in CHF also doesn't depend on CMC. It's really dependent on molar concentration. So you have here surfactants of very different CMC, very different CMCs, but over a log concentration range, you can see that drop in the CHF, and it's pretty much just that drop is all similar across many different surfactants. So just kind of moving along, there can be a huge difference in behavior between the equilibrium CMC behavior and transport limited behavior, right? So big message that I'm trying to broadcast now is that the CMC is really overrated in explaining surfactant enhancement of boiling. Rather, you should look at diffusion timescales, and if anything, maybe you want to use low CMC surfactants, right, to ensure that interfaces are very full and just operate them at very high concentration, around 1 millimoles per liter, something like that. So that kind of wraps up everything I'm going to be talking about pool boiling. I'm going to switch gears completely into a very new topic that is something that I started here in Las Vegas. So if anybody's been to Las Vegas, it's extremely dry. In fact, it is the driest city metropolitan area in the United States. We get the lowest amount of rainfall. And if you've been following the news in the past year or so, Lake Mead is our water source, and it's drying up very quickly and exposing a lot of dead bodies and stuff like that. But this is a serious issue, right? I may have to move out of Las Vegas in 20 years or something because there may be no water. But there is kind of a solution, as you all know, that we can do water harvesting. We can tap the water that's around us, and there's kind of a hidden ocean out there. Now, can this make an impact? Well, there was a study from Nature a couple of years ago by Lord, and this was out of a group from Google, actually. And they did this sort of hardcore data analysis of global weather data and all that, and they figured out that if you could create a hypothetical device that has the performance characterized by this green curve, right? So this is kilograms per square meter per day, or liters per square meter of device footprint per day. If you can have a device that has this performance and it's powered by solar, then you could provide water to 1 billion people in need around the world, right? If you could sort of massively scale this, but this would be the minimum performance requirement. If you look at these circles and the squares, those are state-of-the-art research devices and commercial devices that you can buy right now, right? And they are well underneath this performance mark. So we're not really at a point where this is a sort of mature technology. And if you looked at the work, really kind of started from Evelyn Wang's group with Hyunho Kim in 2017. They came out with that science paper where they used metal organic frameworks, or MOFs. Later, they started transitioning to zeolites. And basically the idea is like you have this kind of sorbent material grab water, and then you can use solar heat to evaporate and desorb that water. More recently, people have been looking at using hydrogels, which are naturally sponge-like polymeric materials. But all of these approaches are generally similar architecturally. It means that you have some kind of sorbent material, which you can think of it as like a battery that you charge, you open it to the atmosphere, it collects all this water, and then you close it to the atmosphere and you heat it up, or apply some kind of solar energy, and it releases that water. And so it's kind of a cyclic thing. And I'm kind of very interested in hydrogels as a material system because as my postdoc, I worked a lot with hydrogels. They have interesting, simply when they're swollen with water, they have the thermophysical properties of water, but they have like solid-like mechanical properties, right? So there's a lot of interest, there's a lot of, cool applications here. But we thought about using hydrogels very differently. We didn't want to do that cyclic approach. We wanted to do it more, like something that could just operate 24/7. So we looked at inspiration from the natural world, and we noticed that, okay, there must be something in nature that's kind of doing water harvesting. Turns out you can look at these Australian tree frogs or air plants, and they will naturally hydrate from the air, or sometimes even thermally condense water, and then they will osmotically absorb water through their skin or their cuticle. So rather than having some kind of polymer battery that absorbs water, we saw that the polymer or membrane really is sort of a flow through layer, right? That doesn't store anything, but just allows water to pass through. So we can think of, evaporation, right? That's kind of the simplest problem. If I take water and I encase it around a hydrogel membrane. So here, imagine I have a hydrogel membrane on the bottom and I have water on top. The liquid that I have stored above it would be evaporating through that hydrogel membrane if I have some ambient wind, right? And that's because there's an osmotic pressure gradient. Another way to think about it is there's a relative humidity gradient. So water moves from high relative humidity to low relative humidity. Now, if we add salt to that liquid phase, then we can lower the equilibrium humidity or lower the chemical potential of that water. And if you make it low enough that the equilibrium relative humidity is less than the ambient, right? So here in Las Vegas, you might get about 30% relative humidity on a humid day. If it's low enough, you have a high enough salt concentration, you can actually get the opposite, where water will absorb through a membrane and into the liquid phase. And this is exactly how plants and animals will hydrate from the air. They basically have a higher osmotic pressure compared to the environment. Now, how would you do water harvesting? Well, if I take a look at this system with the salt, right, that's absorbing water, and let's say I incorporate now into a localized heating layer. And those of you who know, anything about the last 10 years of work in solar desalination, the principle here is that you have to have some kind of thin layer. The first work was really kind of like the plasmonic work, and then out of MIT you had like the carbon layers, and now people are doing everything. 𝗧𝗿𝗆𝗀𝗃𝗃's group does a lot of hydrogel-based stuff. This from sure, this is Harry Atwater, Julia Greer. They also did some very 3D structured hydrogel work. This could be anything, right? And this is an area of research that's been kind of exploding in the last 10 years. So many different methods, right? To have some kind of localized heat, the principle is just heat only the very top layer, you can evaporate it, and then you could sort of recondense that into fresh water. So lots of different proven approaches, and a lot of them are already kind of hitting the solar limit, meaning you can get almost 90% efficiency of like complete conversion of solar heat into evaporative energy, right? So people know how to do this well, so we weren't concerned about whether this is possible, but what we were trying to figure out is, can we capture enough through a bottom hydrogel membrane layer in order to supply enough water to be subsequently distilled, right? So we wanted to understand how you could optimize this process and whether this was even possible to begin with. So we looked at this is a transport problem, right? So now this is a continuous transport problem. You don't have to cycle anything. You can just kind of do like a steady state analysis. And we know that if we look within the gel itself, water has to move down a liquid pressure gradient, right? That's something that we know has to be true as a mechanical engineer. Fluid flow, you go high pressure to low pressure. So we have Darcy's law that describes that, right? So we have permeability and viscosity. Now, incorporating some polymer physics here, we can actually turn this into a gradient of swelling. So S here is a swelling fraction. It basically is the volume fraction of the gel compared to its fully wet state in pure water. So as you add salt water, that gel deswells, it shrinks. And so water moves from high swelling to low swelling, a gradient from high swelling to low swelling. And then finally, we put this in terms of relative humidity, because that's kind of an experimental variable that we can control. And so that swelling fraction is a function of relative humidity. And so we can also put this, this Darcy's law in terms of a gradient of relative humidity, where water moves from high to low relative humidity. And so you can actually build kind of a mass transfer circuit analogy here to understand this mass transfer problem. So through the gel, I can have a resistance through that gel where the driving force is this difference in humidity. And in addition to that, we have a resistance through the vapor phase, right? So this is diffusion through the boundary layer. And so we recognized, looking at this constitutive law, is that we have permeability, we have stiffness, we have viscosity, and we have swelling fraction, and it's dependent on relative humidity. So if we really wanted to understand these terms, there was a whole lot that we had to figure out about the transport behavior of gels. And in particular, this property was very important. We wanted to maximize this. So the permeability stiffness divided by viscosity is known as the poroelastic diffusion coefficient. So we wanted to figure out how can we build very permeable gels, but that are also very stiff, right? Now, when we characterize gels, we wanted to make sure we understood their dependency on humidity, right? Because this is something that in the literature, a lot of people just look at it in their fully wet state or their fully dried state, but nobody really understood how their properties change as a function of swelling fraction and also as a function of relative humidity. And what we sort of figured out, just looking at a lot of old literature, a lot of this comes from the theory from 𝗕𝗲𝗵𝗃, way back in like the 60s and 70s. We know that hydrogel properties will change depending on their cross-linking, right? So the more that we cross-link gels, right, the more tighter their polymer mesh is going to be. And they also depend on humidity, right? So if I take a wet state gel and I dehumidify it, it's going to get a lot smaller, right? And we took this sort of polymer picture of like, okay, looking at these polymer strands, and we think about a gel as being in the semi-dilute regime, right? Where it's not like a liquid, but we have these polymer strands that kind of join together and form sort of a loose network of gels. And the mesh size theory is basically states that all of the properties of the gel essentially come from the average spacing between, or the mesh size, right, which we call 𝗧𝗍. And so you can change this 𝗧 by changing your cross-linking amount. You can change that with your relative humidity, right? And you can relate that to the volume fraction of the polymer, right? So generally speaking, the polymer volume fraction goes with the mesh size to the -4/3. I'm going to, just as in the interest of time, I'm going to go over this very quickly. But we did a deep dive into polymer and mesh size theory. You can relate osmotic pressure to this volume fraction. You can, if you assume chemical mechanical equilibrium, then we can relate this osmotic pressure to mechanical externally applied pressure. which is kind of the pressure that we like to think of more as a mechanical engineer. And ultimately, what we can build is a relationship between the bulk modulus, K, right, the stiffness of a gel, and we can relate that to the polymer volume fraction. So as the polymer network densifies, right, phi-poly to the 9/4, your polymer will get stiffer. And if you know anything about, like, food materials like rice or pasta, right, the less water it has, the stiffer it is. The more they swell up, right, if you cook your pasta too long, it gets way too soft, right, and you don't get that al dente texture. Now, if we can think about it in terms of volume fraction, then we can also relate that to the swelling fraction, which is something that we can more experimentally measure, right? So the more we deswell gels, right, the lower S's, the stiffer our gels are going to be, right? So we can think about this as moving downward on this sort of graph. And so we did some testing with on these hydrogels. We did indentation tests, we did extension and compression tests. We applied Hertzian theory to get the bulk modulus. And we generally saw that, okay, as you increase your cross-linking density, you get your stiffer gels. But we also noticed that if you change the swelling fraction by changing the relative humidity, right? So here on the x-axis, we have the swelling fraction. Left means we have more deswollen gels, right? Closer to their dry state on the left. And we can see that the stiffness followed this 9/4 power that's predicted by mesh size polymer theory or semi-dilute polymer theory. So we sort of, and other peoples have seen this 9/4 scaling as well too. The other thing we did was we varied the polymer type, right, or the monomer type, right? So if you think about these strands, they're built up of individual monomer units, and we can change what that is. And let me just turn on my lights again. They're motion sensing. And we expected that, okay, if we change the polymer type, we might sort of change their behavior a little bit, but we should still see the overall trends. And indeed, what we found is that, okay, within the same monomer polymer type, whether you change their cross-linking or not doesn't actually change their osmotic pressure. So all gels that are made of the same monomer unit, they actually have the same dependence on mesh size and also humidity, right? Their change in osmotic pressure is the same. The only thing that cross-linking does is actually just change the sort of spacing that you see, but otherwise their changes in osmotic pressure are very similar. And we verified that using FTIR analysis, just to show that you're not changing, by adding cross-linkage, you're not really changing the innate chemical structure. This is kind of a sort of a side work from the water harvesting, but we basically came up with a way to predict some of these adsorption isotherms of hydrogels based on this idea that all polymers are kind of similar if they're in the same family. So we could actually predict a lot of their weight fraction dependence on relative humidity. And we did that across 120 different tests, and we could find that, okay, there is actually something here. We can actually predict absorption isotherms. But anyway, that's kind of an aside to sort of understanding how swelling depends on relative humidity and stiffness. But we were ultimately, again, we wanted to bring this back to how can we transport water faster through these gels. So we looked at the network and we realized, all right, if I have a looser mesh, water must be transporting faster through that looser mesh than a tighter mesh, right? That makes a lot more sense. Right, the lower my phi-poly, right, the lower my polymer volume fraction, I should be able to, the permeability should be higher. This also means that we would expect that stiffer gels should be able to move water faster, right? And the inspiration for this kind of came from out of the pandemic. If you ever ordered like takeout noodles, soup, they always give you these noodles in like a takeout container that's like too small, where you can't add all the noodles and all the soup into one container. And even if you did, right? Like it's so tight, right? You can't add a soup, and so like it's really hard to like mix the noodles together with your chopstick, right? And so that's kind of like an increase in stiffness. And if you're like me and you get like something like pho, Vietnamese pho noodles, and you like to add like condiments to your noodles, like like sriracha or something, like you mix it, it doesn't really mix well, right? So it's the permeability of that system is not so great. But if you move everything into a larger bowl and you have enough liquid, right? You have a low enough noodle volume fraction, then it's much easier to mix everything together. So we thought that this kind of helps us understand, as an analogy, what's going on with the polymer networks. By the way, the reviewers hated that analogy, so we had to delete it from our paper, but I want to share it with you guys. Anyway, we came up with a way to actually measure permeability. We had some kind of fluidic cell. And indeed, what we saw is that, okay, as I create stiffer gels with more cross-linking, the permeability actually does increase. In fact, if we put 4 different polymer families together at many different cross-linking amounts, you notice that the permeability in red tends to go down as we increase cross-linker, and the stiffness tends to go up as we increase cross-linker. Meaning there's kind of an inverse relationship between stiffness and permeability. We were always wondering, are these independent or are they dependent on each other? And experimentally, it seems to be that they are very dependent on each other. And we wanted to try to figure out whether there's a deeper reason behind this. So, we applied our theory to, we know that stiffness depends on the polymer volume fraction to the 9/4. Right, and this is something that we verified experimentally. We have this 9/4 scaling. But if we look at permeability, we apply what's known as the 𝗕𝗏𝗃-Kármán relationship. It's kind of a empirical, semi-empirical formula to describe how permeable a particular medium is, assuming it's built up of individual spheres. You can actually come up with the permeability being proportional to the polymer volume fraction to the -2. So that means that the less densified our polymer matrix is, the easier it is for water to go through. And this is something we also independently verified experimentally. Now, if you take these two relations, these two scaling relationships, and you eliminate Phi-poly, we get that the permeability inherently should be almost inversely proportional to the stiffness, meaning the stiffer the gels that I have, the less permeable they should be, right? And, that was a simple scaling relationship, but in a more detailed analysis, we can actually carry all the prefactors and we can figure out what goes in front of that. But we basically verified this across 4 different polymer types. And we put permeability against stiffness on a log-log scale, and we see that the slope is indeed -8/9, right? So this tells us that whatever type of hydrogel you have an inherent trade-off between permeability and stiffness. Now, this took about 2 years of work, right? Doing this sort of deep dive into polymer physics, and we just wanted to make sure that we could actually make a gel that was permeable enough, right? So that 2 years of work led us to this expression right here, which allows us to quantify the actual mass transfer resistance through that gel membrane, bringing us back to that water harvesting system. And now we have everything in terms of experimental measurable properties, and we have a dependence on S, which we can characterize as a function of relative humidity. So we can actually quantify our gel. We can also apply standard vapor mass transfer theory, boundary layer theory in the vapor phase using Blasius boundary layer theory. And we can actually calculate our gel, the resistance of the gel versus our vapor. And what we found is that we can actually make gels that are about an order of magnitude smaller resistance than the vapor phase. So based on our analysis, it seemed possible to make a system that was convection limited, right, or advection limited to the actual where the vapor phase resistance was really the dominant resistance. And the secret to that really is being able to make gels really thin and really strong, and really highly entangled, right? So we have kind of a process to do that. And so, we characterize stiffness, but basically we were able to get about the resistance of the gel being about 1/10 of the vapor resistance. So we expected, advection limited performance. So we built a testing system where we put a very, very salty water solution above a thin gel membrane, and this gel membrane was maybe about 50 microns thick, so it's really thin, really strong. And we flowed humid air underneath, and we varied flow rate, and we noticed that the water was being captured. We imaged the meniscus over time, and you can see that it grows in height. So we're capturing water. And in terms of our performance, we noticed that we're getting a dependence proportional to the square root of velocity, and it's proportional to that relative humidity difference between the solution and the ambient. So this tells us that we are indeed convection limited. In fact, if you look on the bottom right, you have these kind of curves and these data points. Those curves, those lines, are not fits. That's actually from Blasius boundary layer theory, what we expect the actual mass transfer to be. And our experimental points were pretty much right on the theory with no fitting parameters. But we wanted to sort of go the extra mile, and we took our setup outside here in Las Vegas on a couple November days where the humidity was anywhere from 20 to 30%. And we got something on the order of 2 to 6 liters per square meter per day at these very, very dry conditions. And we also we explored the idea of like, okay, if it's convection limited, if we increase convection, we should get better performance. We added a fan, and we found that you do indeed get higher capture. So just to put our results in perspective here, we have here water harvesting rate, right, or water capture rate, I should say, in liters per square meter per day as a function of relative humidity. And if you look at a lot of the state of the art here in these green squares, they often, I'm not going to name names, but they're often in like places like Texas or Boston or next to a lake in China, pretty humid regions where I would question whether our atmospheric water harvesting is, totally needed there. We did it here in Las Vegas, which is much drier, and we need water. And if you compare results to them as a function of relative humidity, it seems we're almost an order of magnitude higher. Obviously, in drier regions, our water capture rate is not nearly as high as it's going to be. On some days here in Vegas, we do have humidities that dip even below 10%, right? So if it's below 10%, we don't really expect to be capturing any water at all, right? But we are looking to ways as to even enhance this even further. So we have our outdoor results here, our indoor results. In the blue triangles, that's actually a commercial device that you can buy. It's like a $3,000 device that you can buy, and but it seems like, at least in terms of the capture, we seem to be beating them quite a bit. So yeah, just to summarize this work, we're doing a flow-through approach rather than a cyclic, absorption, desorption, cyclic type of approach. We're achieving advection limited capture. What we're excited about is, and this work is still under review, so we're hoping to hear some good news very soon. For this work, we kind of did some data analysis, and we looked at world weather data. And on the top here, you can see this is the limit of convection limited water capture if you rely on natural wind and you place this device anywhere in the world. In other regions, you could be getting as high as 70 liters per square meter per day, right? And if we go back to that curve where I said, okay, you have to be above this green curve to reach, a performance metric of, to reach a billion people around the world. The blue data points are our experimental data points, and we seem to be going above that curve, right? So, but obviously there's a lot, techno-economic questions there about how you scale this up, right? So that's all valid concerns. I'm not trying to say that we're saving the world or anything, but I do want to at least introduce that this, there may be a completely new idea here on how to do water harvesting. And the other thing is that we're not actually harvesting water yet, right? We're just doing the capture part. It's really that latter, localized heating, solar desalination. That's something that we still have to implement in our work. But anyway, that's all I want to talk about today. I know I went pretty long, but just want to thank my my lab members and my collaborators and funding agencies. Thank you very much, and I'm happy to answer any questions.
Thank you so much, Jeremy, for this wonderful talk. And yes, please feel free to ask Jeremy any questions. You can feel free to unmute yourself or type in your questions in the chat. I will read the questions.
Jeremy, thank you so much for the very interesting talk. This is 𝗧𝗿𝗿𝗀𝗃𝗵𝗃. I have a couple of questions for you. With regards to your boiling test, that we have multiple other parameters that change. When you look at the Resembles equation, we have multiple other parameters that change relative to the base case, and then you only took the viscosity. Did you look at other factors? Did you try to normalize the data based on other factors?
Yeah, so if you look at the Resembles equation, you have you have like alpha, like thermal diffusivity 𝗕𝗲𝗵𝗃, and trying to think of other sort of physical parameters. But we did take a look at them, and if you look at the surfactant literature, nothing really changed. I mean, you changed it a little bit. You changed TSAT a tiny bit, but we're talking like 1/100th of a degree or something like that for saturation temperature. K is really not going to be changing that much. The only sort of bulk property that people have characterized as changing a lot when you add surfactants is viscosity. And we don't really expect HFG to really be changing, because really HFG is defined by the pure water itself, right? The surfactants don't actually evaporate.
Yeah, the one parameter that I was particularly looking at, it was the C, which is basically, we were doing very careful tests because we saw a big disparity in the boiling data. And then I noticed, and if you look at, let's say, water on brass or copper, that C is 0.006, whereas like on platinum is 0.013. So there's 100% difference between different surfaces. So if your surface properties are changing, why do you not expect that to have an impact?
Yeah, you're absolutely right. And the C is essentially that kind of like the big, unknown coefficient, right? In terms of that Resembles correlation. And so what we're actually doing is if I bring up my let's see. Yeah, so essentially the 1 plus A gamma over gamma max to the B, that is essentially a term that modifies C. You can think of that as essentially an additional coefficient that, like, it's sort of, we're multiplying it against the C. So if you think about the C is not changing, we think, or if you think of C as kind of a nucleation term, right? Depending, because it's surface dependent, we're kind of modifying that with the numerator in this term.
Interesting. With regards to your second question, is with regards to that water harvesting. When you said you're collecting, you showed that you basically absorb and then evaporate on top, and then so did you have a condenser and then you had some other auxiliary equipment to condense the vapor out?
So we actually haven't done any kind of evaporation or condensation, because we're just looking at the capture limited process. So that's really kind of the next step in our research, is incorporating the evaporation and condenser, and which is, a issue that, we say is pretty much solved, or people have done this for 10 years, but it's going to take some unique approaches, I think, to sort of fit to our system. Definitely, it's going to be a challenge.
Thank you.
I think 𝗕𝗏𝗃 raised his hand, so please go ahead, 𝗕𝗏𝗃.
Hey, Jeremy, good to see you and good to see everyone else. So my question is regarding your hydrogel system. What stops the salts in your solution from infiltrating the hydrogel network? As in, like, would your hydrogel become a salty hydrogel towards the end?
So we actually rely on that happening, because if it didn't, then water would not condense into the hydrogel, because otherwise the hydrogel would appear like a high relative humidity or high chemical potential system. So we actually need the salt to penetrate the system to lower the chemical potential very locally at the gel air interface.
Does that change your, like, the transfer? Because I assume the transfer was characterized with a pure water hydrogel, and
Actually, so
yeah, in reality, because I was relying on your schematic, as in the salts seem to be separated.
Yeah, in that schematic, yeah, I couldn't draw that perfectly where the salt was actually inside. Very keen observation there. But okay, so this R gel, we have all of this, all the properties are on the wet state, but we've actually pulled out all the dependencies on relative humidity and salt concentration in that S term. So that 31/12 comes from our theory where we've characterized all the dependencies on salt concentration and relative humidity.
Okay, thank you. Very nice presentation. Yeah,
we can get the properties at the salty state.
So we have some questions from the chat. Again, please feel free to speak out after this question. But I think so. The question. Is there something within the chemistry of the gels that would make the water undrinkable? Water needs to be evaporated, which also helps in purifying the water, but still, have you considered that?
Absolutely. And that's something that we've selectively chose to ignore at this point, because we think of it as a problem we have to solve later. But right now, as is, you would not want to drink this water because you would literally go crazy. So in fact, we use lithium salts, and lithium is a medication. It's like an antipsychotic medication, right? So you would not want to, it would kill you. That being said, the vapor pressures of these salts are very, very, very low. So it means that you can separate them from, separate the water from them very effectively. We don't expect any lithium to sort of come out, but it's certainly something we're concerned about. And we're working with people. There's a lot of water experts here in Nevada because we recycle a lot of water. And so we want to do things like water drinkability testing, potability, and stuff like that.
Hey, Matteo, I'm wondering, since this is 10, should we continue, since this is a really interesting topic and many people are still here.
I guess it depends on Jeremy's availability.
I'm free. I'm on spring break, so I'm happy to sit down.
Be careful.
Yeah. I guess I'll ask. Oh, please.
Hi, thank you for the great presentation. I just had a quick question on if you looked at how the surface wettability was influenced by addition of surfactants, and that in turn helped in increasing the heat transfer coefficient or lowering the critical heat flux.
Yeah, so that's kind of it's a really good question. It's something we've been thinking about I've been thinking about maybe for over a decade now, is like, what's the role of wettability? And if you read the literature, a lot of people say, well, wettability enhances the boiling. But if you look at a lot of the sort of single bubble correlations with boiling and whatnot, generally speaking, the more wettable the bubble is, or the surface is, the easier bubbles will depart from that surface, right? But the other issue is that it means that bubble departure size is going to be smaller. Yeah. And if you do kind of a analysis where, like, okay, the amount of heat flux is proportional to the number of nucleation sites times the bubbles, because you have the volume of bubble size, right? So the more vapor that we generate, the more heat transfer we have. Smaller bubble size, if you look at, you incorporate bubble growth rates being dependent to t to the square root of t, to the square root of t and whatnot, it actually turns out that you get less heat transfer when you have more wettable systems. And this is generally maybe kind of consistent with what people look at with surface structure. If with super hydrophilic surfaces, their heat transfer coefficient actually kind of degrades, but they get really, really good CHF. It's kind of hard to separate these effects perfectly, but my feeling is that the wettability argument actually doesn't really help you, but I think it's primarily due to the fact that you enhance nucleation. And that's something we kind of isolated, back in my PhD work by using the electric field. By basically, we're not changing liquid vapor adsorption. That's still the same. It's the same wettability argument from the liquid vapor perspective. But if you just look at the solid liquid absorption, applying those electric fields just isolates that effect, and that changed our boiling curve drastically. So I think it's primarily nucleation.
I agree with you for the wettability part and heat transfer coefficient, but I think we want the surface to be re-wetted quickly for critical heat flux. So it's a battle between the two. Like you want.
You're absolutely right. Yeah, and that's where because like for CHF, we generally surfactants don't help you. So we're trying to figure out, like, is there a way we could like maybe spatially have it more wettable in certain regions, right? To ensure like, have channels or something. Yeah, so that's a lot of different possibilities there.
Right. Thank you. Just one more question on, because you're using surfactants, which is ionic. When it comes to practical applications, would it cause corrosion? Would it increase corrosion for metals?
If you're using ionic surfactants, I think so, yes.
Okay.
Right. There are things you could do. You could apply a negative potential to make sure that the metal is always being reduced.
Right.
Yeah, I would say I would not recommend using ionic surfactant, like, for sort of long-term use. Probably use a non-ionic.
Okay, thank you. Thank you very much.
Maybe I'll ask a last question. I know, again, in the audience, please feel free to interrupt me. But I think in the interest of time, I'll keep my question short. So Jeremy, a really nice talk. I really enjoyed both topics. In terms of the surfactant enhanced boiling, what do you think of adding those surfactants to like a flow boiling system? I know this is quite different from a pool boiling system, but in terms of further enhancing the heat transfer coefficient and critical heat flux, flow boiling could be a practical system than pool boiling. And but of course the boiling regimes are kind of different. You have annular flow boiling and as well as those bubbly flow. So do you have any comment on that?
Yeah, I really want to do it. I'm just afraid because I know that I don't know what flow boiling system I want to test first, right? And then building that setup. But it's definitely something. It's kind of the next direction that I want to take with this. I mean, one thing I really want to play with is spatial variation of nucleation, right? Like, can you change where the different, like when slug flow occurs or something like that, or as you're transitioning out of it, if you have different heat flux conditions, can you like turn on nucleation like closer to the higher vapor quality region versus the more of the entry region or something like that? There's a lot of different cool variables I could play with, but at this point I don't have like a great sort of really good hypothesis other than like to set up something and then try different things. Yeah, but you're the expert on that, so if you have a particular thing you want to test, definitely we can work on something.
Yeah, that's awesome. Just a quick follow-up question. Have you considered the influence of dielectric fluid? Because I think if your theory mainly focused on the surfactant themselves, but have you considered the solvent, water versus dielectric fluid, and with different dielectric constant, how does that influence your conclusion? Yeah,
so dielectric fluids in general, they're not going to be as soluble with the surfactants that I look at. There are like, if I use a sort of fluorinated fluid, right, like an FC72 or something like that, and I use fluorinated surfactants, which are often used in like firefighting type of chemicals. They're typically not environmentally friendly, but for heat transfer application, maybe there's some, we could think of some usage there. I think there may be a possibility, but this is something that like I think would be a little bit expensive to try to sort of set up that experiment. But yeah, I think in terms of kind of it would take a lot of like trial and error work, but I don't think it's impossible.